So, hello everybody. Welcome to my talk about From Code to Current. My name is Fabian Pflug. A little bit about me. I'm an embedded software developer. I'm very forgetful, and I love home automation. And I also work for Pengatronics, previously Centrix, and we do a lot of embedded software development, and I personally love testing optimization. This talk is not affiliated with Pengatronics, they just sponsored my trip here. This is all my free time here. Because I'm very forgetful, I like to do home automation. And because I do home automation, I was like, I need a sensor to see if my windows are shut in the winter because I want to turn the heating off, or the heating should be turned off automatically if the window's open. And I have like multiple windows at my home, so like I need about 10 window contact sensors, and the current machine is on about $20 a piece. So 200 euros, and I was like, that's too expensive. I can make it cheaper myself. And also, I like to design hardware, and I like a good challenge, so I looked at it. What features do I need? I want to have a button, because why not? Maybe I want to do it for something else. I need a read switch, because I need to see if the window is open or closed. Just put a magnet on there. The read switch would tell me. If you're doing room control and humidity and temperature control, put a temperature sensor in there, could not matter. And I also wanted to, like, if I'm doing it now, put a luminous sensor in there, because I want to see how bright is the room, how dark is the room. I could maybe also use it for lighting control and to switch on the lights if it gets dark at the evening. An LED, because every good project needs an LED. It also needs to have Bluetooth, because I wanted to do it via Bluetooth and the BT Home protocol. It should be integrated into Home Assistant, and the BT Home protocol is already completely integrated into Home Assistant, and it should run on a coin cell. So I made my project. I did everything in KiCad. I made a case in FreeCAD, and I did the software, of course, in Zephyr. That's why we're all here. So if you want to check it out, everything is on there. The slides are also online, so you can check it out later. It has to run on a coin cell, so we have to talk about power consumption. If you want to measure power consumption, you can switch it onto your lab power supply, and it says it doesn't draw any power, 0.00 amps. Awesome, no power consumption, runs forever. Then you put the multimeter on the pass and you measure it again, and then you turn on the LED and you measure the power consumption again, and you write it all down, and then you turn on Bluetooth and you write it all down, and it doesn't change, and you repeat it infinitely, and at some point you recognize that power fluctuates. So doing a multimeter is probably not the best guess. You want to have something like this, a tool that plots power consumption over time. So you can recognize how much power is drawn at what point, and also that accumulates the power the total power that's drawn by the device. So what are there? You could use an oscilloscope and a shunt resistors if you're really cheap and have an oscilloscope at home, because most laboratories start out with an oscilloscope. But I mean, a shunt resistor is like a few cents, measured over time. It would work, but not really convenient. A bit more expensive, but still the cheapest route, the Power Profiler kit version 2. That's what I mostly used, or only used for my talk here. It's quite good. It's $100 a piece, so you can probably afford it. If you've got a little bit more money, I could really recognize the OTA Pro. I would love to have one. If someone wants to give it to me, I'm happy to receive one. It's $1,000 for just the hardware, but they do really good measurements in there. I had the chance to test it out at some point. I got also a lot of recommendation for the Joule scope, a little bit cheap, about $800 I think, but also really good at that. So get one of these, do some power measurements. All I did was here with the Power Profiler kit version 2 from Nordic. Does a good job, good enough job. So what is my power consumption? I measured it before and it looked like this. And the only thing that's relevant for you is the number on the bottom left for 684 microamps on average. If I calculate it, it would be a lifetime of 19.5 days, top right corner. Changing batteries every 19 days, every 3 weeks, not ideal, but yeah, let's see what we can do. So I made a few assumptions. I'm running on a 2033 coin cell. It has a constant voltage of 3 volts over the complete lifetime that never fluctuates. There's no self-discharge. It has 240 milliamp hours. The power measurement over 1 minute is the average over the lifetime of the application. I completely ignore everything that's boot up because like boot up takes a few milliseconds, whatever. And the button and the read contact are never pressed or closed. If I press a button or if I close a read contact, they add about 4 microamps. We can do some complex calculations later, but for our basic assumption, just assume they are never closed. They are always open, and that's quite enough. So what can we do? Zephyr has the config has PM that the vendors can set if they say, we have power management. And then you as a developer can say, config PM, I want to use the system power management. And if you do it and you say like, enable config PM in my config, everything is awesome. But how does Zephyr already do it? So there's an idle thread in Zephyr that says, hey, if config PM is enabled, then I'm going to calculate a time point until the next task based on my task queue, and if everything is scheduled, I'm putting the CPU into sleep mode until this time point. If config PM is not scheduled, then, well, nothing to schedule, just NOP operation. I mean, that's a very simplified thing here. You can't put the CPU into sleep mode until this point. You have to wake it up somehow. So what is actually done is the trigger interrupt at this time point and put CPU to sleep. But a CPU has multiple sleep modes. What one do we choose? I mean, this is an example from an STM32WB55. It has the run mode, the low power run, the sleep, low power sleep, stop, 0, 1, 2, standby, shut down. We're always going to choose the one with highest energy efficiency, so shutdown. But if you do shutdown, then we have to wake up and do all the initialization again, and our RAM is gone. So maybe not shutdown, but standby. Standby is awesome. Yeah, can we wake up on standby? Let's do stop 2, but we have got a 5.7 microsecond wake up time. If you only want to sleep for 2 microseconds, maybe not the best. So we have to do some calculations about what's the best power management, power saving time to get down to what sleep mode do we want to use. So it's not always the fastest time to wake up, it's not always the lowest current consumption, or some external factors. We have to do something. So how do we do it? In Zephyr, we are using our device tree for that, because device trees are awesome, and we are defining power states in the device tree. The device tree now has the min residency US. That's not the minimum time you have to spend in the United States of America. It's the time the CPU should spend in sleep mode in microseconds. So if you have 100 microseconds to spare and you can go to sleep, then choose state 0, stop 0. If you've got more than 900 microseconds, go to stop 2. Zephyr does some magic to calculate this for us and give it to our idle thread. So the power management gets a little bit more complicated, what we had before and what we have now. So we calculate a mode, the sleep mode, based on the remaining time from the time point we want to have the next interrupt, minus now, and then set syslog set timeout to timeout, was previously trigger interrupt at, and then PM set state and and set the state to mode, whatever you have here. If you search the source code of Zephyr for sysclock set timeout and PM set state, you will find the correct implementations for this. So these two functions are correct. Everything else is pseudocode. So awesome, we have the time, we have our sleep modes, and now we can go to sleep. I've activated config PM, and now I've got a lifetime of 51 days. Awesome. Now every 5 weeks, 6 weeks, I don't know, a lot better. But what can I see in here? I see that the CPU is not really sleeping. It's always these high spikes in there. So I have to know about what is my application actually doing. And here currently I've got Bluetooth activated. Your application in Bluetooth is sending advertisement every 100 milliseconds to 150 milliseconds per default configuration. I reduced that to send it to every 5 to 10 seconds because it's a sensor. The temperature is not going to fluctuate every millisecond, and even if it's going to do, I don't want to send it out every millisecond. So I know what I have. I know I have slow-moving values. I send it out every 5 seconds. If one of these advertisements gets lost, or 2 or 3 or 5, I don't care. I measure the temperature like every minute, so the system has 6 opportunities at minimum to send out the values and get one of them to get through. Oh no, every 30 seconds I measure the sensors. I changed it from minute to 30 seconds at some point. Sensor measurement every 30 seconds. I keep it for now. And now it looks much better. The average goes down a lot to 28 microamps, and the lifetime is 446 days. Once a year, awesome. But don't just stop there. Look deeper into it. I mean, it's an average of 28 microamps. If you look at the datasheet of the processor, it says like 4, 3, something like that. So there's a lot of current consumption going on here. Look at it, think about it, what's going on. You have to also think not just about the processor, but also about the peripherals, what peripherals are on your board. Because config PM only controls the CPU, there's another additional switch you can do, that's config PM device, that adds support for power management of sensors. So everything that's a sensor in there, you have to enable config PM device for them to already use something in there. That's also where Zephyr has some disadvantages. Not all sensors have support for it, but also not all sensors need it. There are some one-shot sensors that often don't need it because we're like, enable the sensor, do the measurement, disable the sensor, done. And if you enable the sensor at the start of the measurement, then disable it afterwards. So every time you do a measurement, the sensor gets enabled and disabled. You don't need power management to enable the sensor when the CPU wakes up, disable the sensor when the CPU goes down. So a lot of them don't need it. How does PM device work? We've got our main idle loop, and before we set the state of the CPU, we go to all devices. So we call all devices and say to them, suspend. And then we get a list of all the devices that we suspended. We put the CPU to sleep, and when the CPU wakes up, we have our list of all the devices we suspended and say, resume. All devices, of course not. The idle thread doesn't suspend devices that are busy, because if you're busy, you don't want to get suspended. Uninitialized, if the device is not initialized, you can't put it to sleep mode. That are wake-up sources. So if you want to put down your interrupts to sleep, that wakes up the CPU, maybe not the best idea. And also all the devices that are managed by the runtime. So if you as a user decide in your application, I want to manage this device, and I'm going to do power management for this device, Zephyr idle swap, do not do it, it won't do it. So we enabled config PM devices, and it's the same lifetime. Why is it like that? we've got the mechanical switches. We don't press them, we don't use them, so not software issue. The temperature and humidity sensor is an SHTC3. It's an I2C sensor, it's a one-shot sensor. So it's already power optimized. We've got a luminescence sensor. It's an ALS PT19. I put it on a GPIO to enable it. Then it does an ADC measurement, and it doesn't have support for PM device yet. So if it doesn't have support yet, let's add it. How to add power management to the driver. The first thing you need to do is add PM device DT define inst PM action. So you define in there that you want to have for the, I can't point and talk. At the top you see phototransistor define inst, because I use the DT inst for each status, phototransistor define, that for each instance of my phototransistor in the device tree, this define gets called. And for each instance in the device tree, I want to define that the function called PM action is the function you have to use and you have to call if you do want to do something with power management. Then also, you have to register into the Zephyr main stuff that, hey, this driver can support power management, it does have it, and for this instance, you can have it. So if you forgot the sensor device or DT inst define, the PM device DT inst get, then you won't have power management in there. So, but these two small defines in there, basically the same for everything, everything's done. Nearly everything is done. You have to define the function PM action. It's a basic function, it's called PM action. In my case, it gets a structure for the device, so you know what device you're currently working with, and it gets an enum from the PM device action. You get the enum, you do something based on the enum, and everything is done. So for my phototransistor, I have like device action turn on. If the turns on is called, or if the turn ons get over that, I enable the GPIO. If it's turned off, I disable the GPIO. Pretty easy, pretty small change, pretty fast done. What to expect as action? There are 4 things you can expect. It's turn on, resume, suspend, and turn off. Most of the time, we always see suspend and resume, because during the lifetime of the device, you will suspend the device, resume the device, suspend the device, resume, suspend, resume. This will be called all the time. The turn on action will only be called once. As if you don't do some shenanigans in the kernel and with Zephyr, you can also turn it on from your device application code, but Zephyr itself will only call it once. And the turn off, Zephyr will never call it, because Zephyr will start, it will run forever, and there's no need to turn something off in Zephyr. So if you don't do some shenanigans, turn off is probably never called, and suspend and resume, you will see a lot of times. So turn on, do it to do your installation. Turn off, you can probably ignore it, and suspend and resume, do it pretty good. So what else is there to do? If you're initializing your driver, so in your init function, you have to call PM device driver init, so that the PM device driver also knows this is my function. Call it its turn on function, and we are done. So after we've done this, the device driver is now inside the PM device subsystem registered as I can do power management. I've done it and nothing happened. Why did nothing happen? I mean, we've got PM device enabled and the driver supports PM device, yes. Does the application manage it? No. PM device runtime enabled and driver supports PM runtime? Yes, managed by device runtime. No, PM enabled? Yes, idle thread. It doesn't happen because I lied to you. I never enabled config PM. Why did I never enable config PM? Because I use the Nordic chip. The Nordic chips do not support config PM. They do everything with PM device runtime. So I had PM device runtime enabled from the start. And that's for, they couldn't get anything better when with enabling PM device runtime. If you would run with any other chip like STM, TI, NXP, I don't know what else, they would have done it with config PM. Nordic says, no, config PM, we don't use it. We have our runtime management, everything. What happens if there is no config PM? The device gets suspended and resumed on every CPU wake up and suspend. So whenever the CPU goes to idle, it will put all the sensors into sleep. And if the CPU wakes up to calculate something, it will also wake up all the sensors because maybe they are needed. The CPU can't know about it. Or the idle thread in Zephyr can't know about it. If there's no config PM, the system doesn't manage the device, the idle thread will just say kCPU idle and do everything idle all the time. And the device runtime will do the ref counting about when do I need something. If I need something, I'm going to spend it. If I don't need it, anything, I'm going to put it to sleep. So with device runtime, the application says, oh, I want to do some operation on this device. And the device says, okay, there's a get counter, I need it. The PM subsystem increases the counter. Oh yeah, it's from 0 to 1, so I need to resume the device. Then the device gets resumed, the operation gets done. After the operation gets done, the PM runtime put will be set, the usage counter gets decreased, the device will be put to sleep, and everything will say, oh no, I'm not using it anymore. You can go again, application, do your stuff. So it's like reference counting. You probably know it from the kernel or some other devices. If there's no PM device, it will be done this way. How does power management work without PM? You have to enable the device runtime enable. Pretty easy, call PM device runtime enable, and the Zephyr system will take care of reference counting for you. Whenever you need it, you'll get reference counted 1, and everything is done. So here again, Zephyr takes a lot of burden from you to do everything like that, and everything else is just some small boilerplate for your driver. So I really encourage you, if you're writing a driver, think about power management and put it in there. Get and put the devices when needed. So I've got power management runtime, so I need, say, like, I know at runtime what's needed from myself. So if I do the sample fetch because I'm a sensor, then I have to increase the usage counter by 1, and afterwards I have to decrease it by 1 because I want to do the put. So I snip the declarations and everything like there. So increase the usage counter, do your voltage measurements, whatever you do in your sensor. If after you're done, put it back to sleep and then return the results. So after I've done everything like that, my power consumption goes down a lot more, and I've got now 833 days with 16 microamperes on average. That's pretty good. It's nearly 3 years. I can live with that, and I think it's pretty good. What I can also do is manage the power of the device in the application, because, like I said, if the CPU goes to sleep or doesn't need the thing, it will request the device if I have an idle thread and put it back to sleep if I don't need it anymore. Here I say, I've got my function that reads my ambient light, and before the sensor is read, or before I call the sample fetch function, I'm calling the action resume, and afterwards I'm calling the action suspend. On Nordic, this won't make a change, but on ST and TI and whatever there is, this will now change everything, because the idle thread won't manage the device anymore. the device is now managed by my application, and it's only going to be woken up if I need to fetch the sample. And it's going to be put down to sleep if I don't need it anymore. After sample fetch, it's going to put down to sleep. Because the idle thread will only resume device if it is self-suspended. So let's go to MCU power management. How does power management work on the MCU? You have to implement PM state set. If you go through Zephyr code, git grab PM set word count for the lines 71 times. So it's implemented quite a lot. So 71 CPUs implemented PM state set. You have to have has PM to kconfig for the SoC. You have to configure a timer for wake up because you're going to wake up with some timer. Add CPU power state, the CPU block, and device tree. We already seen them before. And you have to add the power state to the device tree with compatible Zephyr power state. If you search for CPU power states and Zephyr power states in the Zephyr code, you'll find quite a lot of examples for this. So we did that, the PM state set, and we've got the power states in there. And we see that it's quite matched. We have got stop 0, 1, 2, to substate ID case 1, 2, 3. It's the same as the substate ID on the right side, and names are the same, works. Done. It's pretty easy once you know how it's done and what has to be done. And then the question I asked myself was, like, there's also standby. Why is there no standby for the things? Because the RAM is still going on, so the SRAM is on. Why did Zephyr not implement standby? And then I looked at it, and then I looked at it some more, and then it hit me. Zephyr is using timer for wake up. The standby function does not have a timer at some point. So the timers get deactivated during standby. If I can't wake up, I can't go to standby. I can't go to sleep. So I would love to see some code where you use the RTC to do the wake up in there and squinch just a little bit more out of it. Oh yeah, I already said that. We can't have everything. Then I was like, I've got awesome results during my NRF52, and now what can I do? Let's compare different CPUs. What CPU is the best of all of them? And I registered the talk, and I procrastinated, as you do, and then life got in the way, and I was sitting there with the boards, and I wanted to do like custom PCB for all of them, and had so much ambition, and I procrastinated too much. And then I got the boards, and I got the dev kits, and I started working on them, and I decided that the ones in red don't support power management. So I was like, fuck me, I have to implement everything for all of these, and I've got no time, and So future work will be probably implementing power management for all of these and getting to work. If one of the vendors wants to say, hey, we do it for you, hit me up. I would be really happy to see power management working for ST, TI, and NXP, and not just for Nordic. I mean, the old one, the WB55, does have power management. And I talked to the ST guys during Embedded World, and they said, oh yeah, if you don't want to do Bluetooth, use the WB09. That's the most awesome one. Does it support Zephyr? Yeah, everything's working on there. Use this one. I was like, yeah, awesome, give it to me. They were like, here, you have it. Good luck working on it. So, other things to consider. Validate your measurement results. Sensors may be inaccurate after wake up. Analog sensors may take some time to stabilize voltages. What I did here is I used my sensor, my photodiode, and I put an oscilloscope in there. I measured the enable signal, and I measured the photo signal, and I was like, there are 4 spikes because I'm doing 4 ADC measurements and averaging over them. I don't know what's going on, whatever I'm measuring is going to be false. Because as you can see clearly in a oscilloscope scope, this voltage is still rising. So whatever it is wrong. So not just optimize power measurement, validate what if power measurement means you do, looked at this really correct. So what I did was I added a delay between enable and measurement. If I call the PM action resume, I say the earliest time at which I can sample is now plus some sample delay in microseconds. I can configure it using device tree there, and then I know that if you wake me up at some point in the future, until some point in the future, you can't do some measurements. So if you do sample fetch, what I did here was k-sleep. I sleep until the earliest data point. Because it's an absolute point in time, if it's already passed, k-sleep will just do nothing. So after this, you can see that I clearly have a rise on the beginning, and one block inside of this is the whole measurement from the old time. So I now sleep some microseconds. It's maybe a bit too long, but over optimization, we don't want to do that. We've got some stable values at the end. We measure something, and then we turn it off again. And it's still just a little bit over 1 millisecond, so don't fret the things. Okay, some of the last things know about parasitic devices. Can any of you guess what happens at this time point? No, I did something with hardware. No? No, not with my hand on. I connected to J-Link. So if you're using this with dev boards, the J-Link is always connected. So, I mean, the measurement results like 40 microamps, just because the J-Link is connected. And I know what you're thinking. I'm just going to turn off the J-Link. That's going to be awesome. I connected the J-Link without power. So really have all your other measurements stuff disconnected. Don't have a probe in there, don't have anything in there. If you're doing power measurements, disconnect everything. Just have your device under test in its barest form. Some best practice I want to emphasize again, measure before and after optimizing anything. So before you optimized anything, take a measurement before, take a measurement afterwards. Did it do something, or did you just enable some config that has no real application in the real world? Talk to your hardware people. Bad hardware will never be good with just software. If you've got hardware that's really bad and just consuming amperage, it's going to be consuming amperage all the time. Software can't fix it. Do one step at a time when optimizing. Premature optimization is the root of all evil. We all know it. We never think about it. Validate that your sensors still work correctly. Disable all subsystem and devices that you do not need. Especially the Nordics chips are very power hungry if you enable UART. They consume like, what is it, 40 microamps or something like that, just for having UART RX enabled. You don't send anything out, just having UART RX enabled. It's like insane. I mean, on the older device, I haven't tested it on the 54 now. Try to find the sweet spot between energy consumption and performance, and don't set config PM and config PM device per default. It could be nice to have energy consumption reduced, but Zephyr doesn't know how long it takes to wake up devices. There may be sensors that are integrated in the first measurement after resume, and the waking up and suspending devices can take time. And if you have a lot of sensors in your device tree, then your accuracy can go down. So validate what you're doing, not just blindly, it's optimizing, it will be done perfectly. Awesome. Some fun with graphs. You can see a lot of things during power measurements. I let the LED blink twice during boot up, and you see like, you can see it in power measurement graph very good. The LED blinks twice after boot up. And also there's MCU boot and then going to Zephyr and start up and then afterwards sleep and idle. If you zoom in a lot, you can also see more. This was one Bluetooth beacon sent out. I've got measurements, the measurement of the sensors, then I've got some idle time, and then the Bluetooth was actually updated, and it was sent out and received. And if you zoom in even more on the BLE receive, I mean, this was with like only 10,000 samples per second. If you go to 100 or 60,000 samples per second, you can, in this last peak for the BLE receive, see 3 different peaks, because Bluetooth does 3 receive cycles. Yeah, that's it. Are there any questions? Yeah.
It seemed like there was a periodic tick interrupt happening. That's the periodic spikes.
Yeah.
Is there a way to get around that, tickless mode?
I don't know if it's periodic ticks or if it's just inaccuracy in measuring, because like the ticks here are in the voltage range of 1 microamp to 10 microamps. So it could also be the DC-DC converter, it could also be something like that. Not really sure what exactly this is.
It looks really a lot like a tick interrupt. They tend to look like that.
Yeah. It could be a tick interrupt. I don't think it's a tick interrupt because, yeah, no, I don't think it's tick, because the ticks would be either more different, more cleaner separated, or smaller together. I think it's a DC-DC converter.
You see depth overloading.
Yeah.
Did you consider when choosing sensors a different interface like SPI to further reduce power consumption?
No, I did not. I was like, I'm doing my first thing, go for it. And then after I had it, I was like, I'm doing some measurement results now, and I wanted to see what's going on there. You could probably do that, and it would be a good idea to do that. It's like I said, talk to your hardware people. Bad hardware doesn't compensate for good software. At the back?
Do you have any idea why the DT idle states are Zephyr specific?
Again.
Do you have any idea why the DT idle state for CPU are Zephyr specific and not generic?
Why the DT idle states are Zephyr specific and not generic? I don't know how to answer these questions. I mean, do you think about having them ported from Linux, or?
DT is not supposed to be Zephyr specific.
Yeah.
And so, yeah, we do have idle states in Linux as well, and they look pretty similar.
So I have no idea why Zephyr does it in this way. Wasn't involved in when the pull request got merged. There was another question there.
If you consider the internal resistance of the coin cell versus the power consumption needed for GX and RX, so in terms of voltage peaks that may run in order or in magnitude of the brownout, especially when the coin cell drains.
Yeah, like I said in the first slide, I'm ignoring that the coin cell has any internal resistance and anything like that, because I didn't do the measurement with the coin cells in there, but have a power supply in there and power everything with a LED power supply, and then just like look at what the current consumption. So I want to use this device with a coin cell, and that's my target, that's where I want to optimize for, and then I want to know how long can I run them, but what are there, what's going on there, I didn't optimize for that. If I use tracing to see what spikes contribute to what processor said. No, I did not. I mean, there are very few spikes. If you go back a little, you see that there are only some spikes in there at all. If I ignore the boot up sequence, I mean, that's powering on the device, boot up, blinks twice after boot, and then there are only like very few spikes in there at all. And I can, just looking at them, I see that that's Bluetooth, that's power measurement as a measurement of sensors. And I also did some validation where I'll have like a logic analyzer connected to it, and I see like, oh, here, this spike, the logic analyzer said that the sensor was active, so the enable pin for the sensor was active. So I know that what corresponds to sensor measurements and the other Bluetooth is like you see here, they're very, very distinct to see if you measure in the Bluetooth what exactly is going on there. So I did not do anything for tracing because, I mean, the application is really simple. It's like 100 lines of code to just measure the sensor, put it in there, and send it, update the BLE advertisement data.
Can you talk a bit about, so you looked, we saw the CPU states, and you talked about standby.
Mm-hmm.
There's one afterwards, which is shutdown.
Yeah.
Do you have any support in Zephyr for that? Like shutdown, which would be called hibernation, in a sense, where you wake up and just wake up from nothing?
Yeah, there's support for shutdown in some of the CPUs, but then you have to call shutdown explicitly. But if we go back one slide, the wake ups, I mean, after shutdown, you have to wake up again and do the initialization, and the initialization sequence is like really power hungry if I compare it to everything else in the graph. So if I did a shutdown to just get some more juice out of it, the low power states wouldn't not wait off the initialization sequence. So shutting down this device, it would make sense if you do like, oh, the next 6 months I'm not going to do anything. Yeah, do a shutdown. But for like, I'm just going to idle here and have Bluetooth advertisement like every minute, don't do shutdown. And for, like I said, for standby, there's currently no support in Zephyr.